Hello. Hello and welcome to this video. In this video, we will look at subquery expressions. We have covered window functions and merge functions. So we have not seen the example of any of these. Therefore, we will see the example. We will not be able to cover the full example, but we will proceed as much as we can. Right? So subqueries are very interesting. They are quite powerful. Back in the past, subqueries were not as efficient. The databases implementation was not very efficient. But now subqueries are quite powerful and they perform on par with joins. Personally, if you ask me, I find subqueries easier to understand and reason about than joins. If I have to write a complex query, I will always prefer subqueries over join. Joins are little for me. Joins are a bit harder to understand for me. It may be easier for you. So let's get started with subquery expressions. This section describes the SQL compliant subquery expressions available in PostgreSQL. All of the expression forms documented in this section return Boolean results. The first one is exists. The argument of the exist is an arbitrary select statement of subquery. The subquery is evaluated to determine whether it returns any rows. If it returns at least one row, the result of exists is true. If the subquery returns no rows, the result of exist is false. The subquery can refer to variables from the surrounding query, which will act as constants during any one evaluation of the subquery. The subquery will generally only be executed long enough to determine whether at least one row is returned, not all the way to completion. It is unwise to write a subquery that has side effects such as calling sequence functions. Whether the side effects occur might be unpredictable. Since the result depends only on whether any rows are returned and not on the contents of these rows, the output list of the subquery is normally unimportant. A common coding convention is to write all exist tests in the form of exist select one where. There are exceptions to this rule, however, such as subqueries that use intercept. This simple example is like an inner join on column 2, but it produces at most one output row for each tab 1 row, even if there are several matching tab 2 rows. So our query is select call 1 from tab 1 where exist, select 1 from tab 2 where call 2 is equal to tab 1 dot call 2. So tab 1 has column 1 and column 2, and tab 2 has column 2. So first the inner query will exist, will run, and we will select one from tab 2 where column 2 of tab 2 is equal to column 2 of tab 1. And if there is any such row, then on finding the first row, it will bail out, and then this query will run and it will select column 1 from tab 1. Now we have inquiry. I think it is quite useful and very important. The right hand side is a parenthesized subquery which must return exactly one column. The left hand expression is evaluated and compared to each row of the subquery result. The result of n is true if any equal subquery row is found. The result is false if no equal row is found, including the case where the subquery returns no rows. Note that if the left-hand expression yields null, or if there are no equal right-hand values, and at least one right-hand row yields null, the result of in construct will be null, not false. This is in accordance with SQL's normal rules for Boolean combinations of null values. As with exist, it is unwise to assume that the subquery will be evaluated completely. So we have row constructor in subquery is not very helpful, but when we will see examples, you will see what all this means. The left-hand side of this form of int is a row constructor as described in section 4.2.13. We have not read that. The right-hand side is a parenthesized subquery, which must return exactly as many columns as there are expressions in the left-hand row. The left-hand expressions are evaluated and compared row-wise to each row of the subquery result. The result of n is true if any equal subquery row is found. The result is false if no equal row is found, including the case where the subquery returns no rows. As usual, null values in the rows are combined for the normal rules of SQL Boolean expressions. Two rows are considered equal if all their corresponding numbers are non-null and equal. The rows are unequal if any corresponding numbers are non-null and unequal. Otherwise, the result of that row comparison is unknown. If all the per row results are either unequal or null with at least one null, then the result of n is null. Then we have not n, which is the negation of n. The right-hand side is a punch-side query which must return exactly one column. The left-hand expression is evaluated and compared to each row of the subquery result. The description is basically same as the n1. The result of not n is true if only unequal subquery rows are found, including the case where the subquery returns no rows. The result is false if any equal row is found. Note that if the left-hand expression yields null, or if there are no equal right-hand values and at least one right-hand row yields null, the result of the not in construct will be null, not true. This is in accordance with the SQL's normal rules for Boolean combinations of null values. As with exists, it is unwise to assume that the subquery will be evaluated completely. The left-hand side of this form of not in is a row constructor as described in section 4.2.13. The right-hand side is a punch-side subquery which must return exactly as many columns as there are expressions in the left-hand row. The left-hand expressions are evaluated and compared row-wise to each row of the subquery result. The result of not in is true if only unequal subquery rows are found, including the case where the subquery returns no rows. The result is false if any equal row is found. As usual, null values in the rows are combined for the normal rules of the SQL Boolean expressions. Two rows are considered equal if all their corresponding numbers are non-null and equal. The rows are unequal if any corresponding numbers are non-null and equal. Otherwise, the result of that row comparison is unknown. That is null. If all the per row results are either unequal or null with at least one null, then the result of not n is null. Then we have any and sum. The right-hand side is a fancy-side subquery which must return exactly one column. The left-hand expression is evaluated and compared to each row of the subquery result given the using operator, which must yield a Boolean result. The result of any is true if any true result is obtained. The result is false if no true result is found, including the case where the subquery returns no rows. Sum is a synonym for any. N is equal to any. Note that if there are no successes and at least one right-hand row is null for the operator's result, the result of the any construct will be null, not false. This is in accordance with SQL's normal rules for Boolean combination of null values. As with exists, it is unwise to assume that all subqueries will be evaluated completely. Again, we have row constructors, and it is described in section 4.2.13. The right-hand side is a punch-side query, which must return exactly as many columns as there are expressions in the left-hand row. The left-hand expressions are evaluated and compared row-wise to each row of the subquery result using the given operator. The result of any is true if the comparison returns true for the subquery row. The result is false if the comparison returns false for every subquery row, including the case where the subquery returns no rows. The result is null if no comparison with the subquery row returns true and at least one comparison returns null. And we will see section 9.25.5 for details about the meaning of a row constructive comparison. Then we have all. So the right-hand side is a parenthesized subquery which must return exactly one column. The left-hand expression is evaluated and compared to each row of the subquery result given using the given operator, which must yield a Boolean result. The result of all is true if all rows yield true, including the case where the subquery returns no rows. The result is false if any false result is found. The result is null if no comparison with the subquery row returns false, and at least one comparison returns null. Not n is equivalent to not equal to all. As with exist, it is unwise to assume that the subquery will be evaluated completely. The left-hand side of this form of all is a row constructor as described in section 4.2.13. The right-hand side is a parenthesized subquery which must return exactly as many columns as there are expressions in the left-hand row. The left-hand expressions are evaluated and compared row-wise to each row of the subquery result using the given operator. The result of all is true if the comparison returns true for all subquery rows, including the case where the subquery returns no rows. The result is false if the comparison returns false for any subquery row. The result is null if no comparison with the subquery row returns false and at least one comparison returns null. And again, we will see section 9.25.5 for row constructor comparison. Then we have single row comparison. The left-hand side is a row constructor as described. The right-hand side is a parenthesized subquery which must return exactly as many columns as there are expressions in the left-hand row. Furthermore, the subquery cannot return more than one row. If it returns zero rows, the result is taken to be null. The left-hand side is evaluated and compared row-wise to the single subquery result row. So we'll stop here and we will look at the example. So if you have not watched my previous video, you should go and watch because we are going to cover the window functions and my support functions examples here. So let me get rid of this and let's look at the example I prepared. And this is the PostgreSQL. So what I will do is I'll quickly drop the database which we have been using, and I will create the same database so that we are fresh on the database. We are now connected to the text. Now we create departments and we paste it here. Okay. Where is the error? Okay, we have the table created and then we insert into this database 4 departments: engineering, sales, marketing, and support. And we have 4 rows inserted. And now we'll, so you see the departments are 2 columns, department ID and department name. Now we will create employees table and we paste it there and the table is created. The employee ID is integer, primary key, employee name, text not null, department ID is integer, not null, references the department ID of the department table. And hard date is date, not null, salary is numeric, not null. So we now insert employees: Alice, Bob, Charlie, David, Eva, Frank, Grace, Henry, Irene, Jack, Karen, Leo, Maria, and Nathan. So we take this and we paste it here. Okay, so paste it again. There is error in line 27. Somewhere we have bad data. Okay, we have to leave bad data. So we copy it again and we paste it. Okay, we have 14 rows inserted. Now we create a products table which has product ID, integer, primary key, product name, text not null, category text not null, and unit price is numeric not null. So we copy and paste this. And then we insert into this products, laptop, mouse, and other things, cloud sync and whatever. And we have 7 rows inserted. So we have 3 tables now: departments, employees, and products. Now we create a table sales, which has sale ID, big integer, primary key, should big serial, employee ID, integer, not null, references employees, employee ID, product ID will reference product ID in product, sale date will be date, not null, quantity will be integer. We will check that quantity is greater than 0, and total amount is numeric. We will check total amount should be greater than 0. So we create this table, and our table is created. Then we insert into sales the sales data. There is a lot of data we have to insert. So, okay. So, okay. We copy this. That will be all right. So we have 43 rows inserted. Now we first look at the first in the function row number. Okay. So we are selecting employee name, salary, and row number over. We order by salary descending, okay, as salary position from employees. So this will be a salary position and this will be row number. Now this numbering, to achieve this row number, we are ordering by salary. Okay, and we select from employees and we are ordering by salary again. So both are ordered by salary. So we see this. Okay. And we have salary position 1, 2, 3, 4, 5, 6. So these are the row numbers. Okay. And ordering is by salary. All right. Now we do a row number within each department. So we have department name, employee name, salary, row number over. Now we do a partition here. So partition by E dot department ID. So this partitioning will kind of group them by the department, okay? Order by salary descending as department position. And then we have employees P, we have a join department D on department ID should be equal in the department's table and the employees table, and we order by department name and department position. So we select this and create this. So this is relatively complicated query, so pay attention here. I will repeat this. We are selecting department name, employee name, and salary. Row number over partition by department ID. So we are partitioning by department ID here, department position. And we are ordering by salary descending. So for each department, salary will be descending. And we select this from employee C. The join is simple. That is department ID and employee ID, department ID of employee and department should be equal. And finally, the overall order will be by department name and department position. You see, engineering is selected first, and we have position 1, 2, 3, 4. And then marketing, position 1, 2, 3. And then sales, position 1, 2, 3, 4. And support, position 1, 2, 3. So this kind of query will help you a lot. And then we look at RAM. So we select employee name, salary, and over order by salary. So it is quite similar to row number. So see what this gives us. So rank gives us similar to row number. It is continuous in nature. Okay. Now, okay. So the extra hint is that rank produces gaps after ties. So now what we have here is, now I will not describe what rank does and dense rank does, because that we had covered when we read the documentation. Okay, that is why I'm not describing all the functions, because if you're not watched my previous video, then you should go ahead and watch those when we covered the documentation of PostgreSQL. So rank we are ordering by salary and taking it as rank position column. Then we have dense rank, which also we are ordering by salary position, and then we order everything by salary. So You see, for this rank position and dense rank position, both are same. But because I don't see there are any ties. Okay. Now we have dense rank. So instead of the previous one, we are doing a dense rank partition by department ID or by salary. We select this as salary rank, and the join is same. This time ordering is by department name and salary rank. So we take this, and we have kind of similar output which we had earlier. Then we have percent rank. So we select percent rank, order by salary as relative rank, and then we order by salary. So you see the percentage rank of every employee. So with this gap which you see 0.7691538, so it is basically divided by the number of rows between 0 and 1, okay, as we had studied in the documentation. Now we have cumulative distribution. So like relative rank, we compute cumulative distribution. So again, now we look at entile. So we select entile 4 over, and it is salary quartile, right? So you'll see what happens. We are grouping the employees into 4 groups here. Entire 4 will convert the employee into 4 groups. If you want, you can convert them into more groups. So for example, you can convert them into 5 groups. Now when you convert into 5 groups, since there are 14 rows, first 4 will be 3 each, and then 2 will be in fifth row. Right. Now we compare each cell with the previous cell. So how do we do that? We use the lag. And we look at total amount over order by sale date, sale ID as previous cell. So the lag function will give us that. So we run this, and we have the table here. It's quite big. So when you do the practice, you examine this carefully. Now we have lag again, but this time we complete the difference as well. Okay. So we will have a difference column as well. So we can see the difference between the previous sale and that sale. Then we have lag with partitioning. Okay, now we are partitioning by employee ID. So employee ID's lag will be grouped in one place. So see, employee ID 101 is grouped here. Okay, and 1102 and 103 and so on. So this kind of grouping you can do. Then we have lag with offset and default. So we run this, and you see sale 2 rows earlier. So again, you can see that we are ordering by employee ID. So 101 has come first, and 102 has come second, and so on. Then we have lead, which is kind of reverse of lead, a lag. So you'll see kind of reverse output of that. And then we have lead with partition, similar to lag with partition. So again, it is kind of reverse of lag. Then we have lag and lead in one place, where lag is the previous sale and lead is the next sale. So this we do over W. So what is W here is W, we are partitioning by employee ID and ordering by employee ID and sale date. You can see lag and lead is one row, and you can see what is going on here. So you see this sale is 2400, and this sale is 2400. So this is next sale is 2400, and then this is 1200 and 3000. But if you see the previous sale, so for 3000 previous sale is 1200, and for 1200 previous sale is 2400. For this 2400, this is 2400. For 1200, this is 2400. And then for this, we don't have a previous cell. So lag and lead you can see in this way. Then we have the first value over partitioning by employee ID. So we look at the first value and we have that. Okay. Now first sale date we can compute here. The first sale date is listed here. Right. Now if there is we are computing last values, there is something important here. The default frame ends at the current row divided by current row. Therefore, this is not only the final row in the partition. So what we are selecting is last value over total amount over partitioning by employee ID, ordering by sale date, sale ID, and finally sales will be ordered by employee ID and sale date. So that is what our last value is computed here. Okay. Now the actual last value of the entire partition. Remember, we are partitioning by employee ID here. Okay. You see, this last value is the sale amount. And so 102, 2400 is the final sale amount. So that's how we computed it. And then we have the nth value, total amount from a 2. And so this description, again, you need to look at the previous video. So we compute nth value, and the 2 one is the 2400 for this. For 102, it is 3000, and for 103, it is 4000. To see how we are selecting the second value. So this is quite big a script, and I will cover the remaining example in the next video. Okay. So we are at nth value. So I don't want to make this video very large, and this SQL script will be in the gist. Let me create the gist for you. So this com, and we have window dot although it is not entirely window because we have subqueries in the end. As far as I remember, subqueries are there. Maybe subqueries are missing. It's what I don't see subqueries. Okay. Window, we'll call it window.md because most important examples are window examples. We paste it here, and in tomorrow's video, I will finish the window functions as well as subqueries. Okay. So this link will be in the YouTube description. So you can download this video from there. So with this, I will end this video here, and I hope that you have enjoyed this video and found it useful and you got to learn something. So with this, again, I will repeat that if you could not follow this script, then you should go back and watch my previous videos where we went through window functions and multiple functions. So with this, I'll end this video here, and I'll see you tomorrow in the next video with the complete example, or rather the remaining part of example and subqueries. So thanks a lot for watching the video, and keep learning, stay curious, and most importantly, enjoy.